Welcome back. In the last lecture, I introduced ammonia water systems and we discussed the properties of binary mixers of ammonia water. This lecture is a continuation of the earlier lecture, and in this lecture I will discuss in detail the working principle of ammonia water systems. So, the specific objectives of this particular lesson are to explain the working principle of absorption systems using ammonia water pair with some of its salient features, explain the principle of rectifying column, discuss briefly the steady flow analysis of the system, explain the principle of triple fluid absorption systems, and finally compare absorption and compression refrigerant systems. At the end of this lesson, you should be able to explain the working principle of ammonia water system and its salient features, explain the operation of rectification column with enthalpy composition diagrams, perform steady flow analysis of the system, explain the basic principles and features of pumpless triple fluid systems, and finally compare compression refrigerant systems with absorption systems. So, let me give a brief introduction. Absorption refrigerant systems based on ammonia water, they are one of the oldest refrigerant systems which were developed at the end of 19th century. These systems can be used for both refrigeration and air conditioning applications because the ammonia is the refrigerant here, so it has a very low freezing point and you do not have the problem of like in water where it cannot be used for sub-zero temperatures. And these systems are available in very small refrigeration capacities to very large refrigeration capacities, and mainly they are used in domestic refrigerators in pumpless form and also in large cold storages. Now, the operating pressures in ammonia water systems are much higher than atmospheric. So, you do not have the problem of air leaking into the system. This is one of the typical problems of water lithium bromide systems which operate under vacuum. So, you always have air leaking into the system. This problem is not there with ammonia water systems. And you also do not have the problem of crystallization, which was again a typical problem with water lithium bromide systems. However, ammonia is not compatible with materials such as copper or brass. So, normally the entire system is fabricated out of steel, and ammonia is both toxic and flammable. So, we need to take certain safety precautions while designing and operating these systems. Now, let me explain the operating principle. Major difference between this system and water lithium bromide systems is that you use 3 additional components here, and these 3 additional components are a rectification column, a deflagrator and a subcooling heat exchanger. Without rectification, vapor leaving the generator may consist of 5 to 10% of water, and the need for rectification was explained in the last class. If you do not rectify the vapor, you have 5 to 10% of water in the refrigerant circuit. This will create problems like non-isothermal condensation and evaporation, and it will also increase the evaporator temperature. It increases the circulation ratio. So, ultimately the system performance suffers. So, in ammonia water systems, they have to be designed in such a way that most of the water is confined to the solution circuit only, and in the refrigerant circuit you have almost pure ammonia. So, this requires the use of a rectification column. Okay, and the rectification column consists of the generator, a rectifying column and deflagrator. So, this is something different from water lithium bromide systems. Okay, and what is the function of subcooling heat exchanger? The subcooling heat exchanger is used to increase the refrigeration effect and also to ensure that only liquid enters into the refrigerant expansion valve. Now, let me explain the operating principle. Okay. So, as I mentioned, you have the for basic components here, you have the evaporator, condenser, absorber, solution pump and generator. In addition to these basic components, you also have an additional heat exchanger here, a subcooling heat exchanger, and you have what is known as a deflagrator here, and you also have a rectifying column. Rest of the components are similar, like your solution pump, expansion valve, liquid suction heat exchanger. All these components are similar to water lithium bromide systems. So, the working principle is like this. Let us begin with point 14, which is nothing but the exit of evaporator. So, at this point you have low temperature, low pressure refrigerant vapor. This low temperature, low pressure refrigerant vapor enters into the heat exchanger 1, where it exchanges heat with the refrigerant liquid coming from the condenser. In this process, the refrigerant vapor gets superheated and the liquid gets subcooled. So, this is something similar to your liquid suction heat exchanger used in Vapour Compression Refrigeration Systems. So, okay, so what comes out of the heat exchanger is a superheated vapor still at low pressure. So, this superheated vapor now enters into the absorber. In the absorber, it comes in contact with the weak solution coming from the generator. So, this is your weak solution. Okay. Weak solution here means weak in refrigerant. So, this weak solution and ammonia vapor coming from the evaporator, they come in contact in the absorber and the refrigerant is absorbed in the absorber. Since this is an exothermic process, heat is rejected in the absorber, and what you have at the outlet of the absorber is a strong solution at 0.2. Okay. So, at 0.2 you have a solution that is rich in ammonia. Okay. This is still at low pressure. So, this strong solution is pumped to the generator pressure using a solution pump. Okay. So, in the solution pump it is pressurized, and this high pressure solution, which is still at low temperature, enters into this heat exchanger 2. Okay. In the heat exchanger 2, this is nothing but your solution heat exchanger, where it exchanges heat with the hot solution coming from the generator, that means at 0.6. Okay. In this process, this strong solution becomes preheated. So, it comes out at a higher temperature. So, temperature at 0.4 is much higher than temperature at 0.3. So, this preheated strong solution enters into this rectifying column, and in this rectifying column this strong solution falls through this rectification column, and it ultimately comes to the generator, where you supply the heat, and because the heat supply, vapor is generated, and this vapor gets rectified in the rectification column and deflagmator, and finally what you have at the exit of this deflagmator is almost pure ammonia, that means almost about 99.9% ammonia. Okay. So, this 99.9% ammonia vapor, which is at high pressure and high temperature, goes to the condenser. It condenses in the condenser by rejecting heat of condensation QC to external heat sink, and it becomes a high pressure liquid 0.11, and the high pressure liquid at 0.11 now flows through the heat exchanger, where it rejects heat to the vapor coming from the evaporator. So, in this process it gets subcooled. So, at 0.12 you have subcooled refrigerant liquid still at high pressure. So, this subcooled liquid refrigerant at high pressure is expanded in this expansion valve, and the resulting mixture of liquid and vapor at 0.13, which is now at very low temperature and low pressure, enters into the evaporator. It takes the heat from the refrigerated space, provides the refrigeration effect QE, and in this process it becomes a vapor, and this vapor goes back to the heat exchanger, and that is how the refrigerant circuit is completed. Now, coming back to the solution circuit, in the generator refrigerant vapor is removed from the solution. So, what you have at the exit of the generator is a weak solution 0.6. So, the weak solution at 0.6, which is quite hot and which is at high pressure, now flows through this solution heat exchanger, where it gives off heat to the strong solution coming from the absorber. So, in this process the temperature of the weak solution reduces from T6 to T7. Still, since this is still at high pressure, its pressure has to be reduced to that of absorber pressure. That takes place in this solution expansion valve. So, at the exit of the solution expansion valve you have low pressure weak solution, that is 0.8. This low pressure weak solution now comes in contact with the refrigerant vapor coming from the evaporator, and absorption takes place, and that is how the solution circuit is completed. So, this is the working principle of ammonia water system, and this is actually you can call it as a single stage ammonia water system. Okay. This is a typical system used in most of the commercial installations. Okay. So, the analysis and analysis of this system I will explain a little later. Before coming to the steady flow analysis, let me explain the working principle of the rectification column. This is the rectification or the rectifying column, which consists of the three components, and let us first concentrate on this rectification column. Before explaining that, I forgot to mention one thing. In the deflagmator, the refrigerant vapor rejects some of the heat to a heat sink. That means some heat rejection takes place in the deflagmator. That heat rejection is given by QD, and due to this heat rejection, some of the solution condenses in the deflagmator, that is known as reflux. Okay, so I will explain this while explaining the rectifying column. Okay. So now let me just summarize the energy flows into and out of the system. We have seen that high temperature heat input is given to the generator QZ, and low temperature heat input is given to the system at the evaporator. This is nothing but your useful refrigeration effect QE, and then heat rejection takes place at absorber, condenser and deflagmator. Deflagmator is a new component here, and a small amount of work input is required to run the solution pump. So these are the typical energy flows into and out of the system. Now let me explain the principle of rectification. So as I explained already, the rectification system consists of generator, a rectifying column and a deflagmator. So let me show the schematic of it. So you can see that the whole thing is your rectification system. It consists of 3 components: generator, and this is your rectification column, and a deflagmator. Deflagmator is at the top of the rectifying column, and heat is supplied to the generator. High temperature heat QZ is supplied to the generator via a heating medium. So because of this, vapor is generated. Okay, so vapor is generated and vapor moves up. This vapor comes in contact with the strong solution coming from the absorber. Okay, so there is a direct contact between the strong solution and the vapor in this lower portion of the rectification column. As a result, we will see that this vapor becomes rich in ammonia. That means by the time this vapor comes from this point, the lower portion, to this point, it becomes stronger in ammonia, and further enrichment takes place in this column, where the vapor comes in contact with a reflux that is coming from the what is known as the reflux condenser. Sometimes the deflagmator is also known as reflux condenser. Reflux condenser. So in the reflux condenser, what happens is some heat is taken out of the hot vapor by using a cooling water, and during this process some of the vapor condenses. That condensed vapor is called as reflux, and due to gravity this falls down, and as it falls down it comes in contact with the vapor that is moving up. That means the descending liquid comes in contact with the ascending vapor, and during this process further enrichment of the vapor takes place, and ultimately what you have at the exit of the rectification system is almost a pure ammonia. That means, as I already mentioned, you have about 99.9% ammonia in the vapor. Okay, it's almost pure ammonia. Okay, so in order to achieve this, you have to design the rectifying column properly. Now let us concentrate on each component. That means the lower portion of the rectifying column, and let us see how what is the working principle of this and how do we show this on enthalpy composition diagram. Similarly, we will look at the upper portion and explain the working principle and show this on enthalpy composition diagram. Okay, so as I said, you have seen that rectification system consists of the 3 components, and a heating medium supplies the required heat input, as I have already mentioned, to the generator, and heat QD is rejected to the cooling water in the deflagmator. Okay, so at one place you supply a high temperature heat, at another place you reject some of the heat. Now let us look at the generator plus lower part of the rectification column. Okay, first let me show the working principle. Okay, so you can see here the generator here. This is generator G, and this is the lower portion of the rectification column. Okay, so you have in the generator you have you have a solution of ammonia and water. Okay, and from the top strong solution of ammonia is coming from the top. Okay, so this is what is coming from your absorber. Okay, and heat is supplied to this solution bath at the bottom portion. You are supplying the heat to the solution here. As a result, vapor is generated. So this is the vapor moving up, and vapor has a initial concentration of zeta WV. Okay. So, this vapor moves up, and as it moves up, it comes in contact with the liquid that is coming down. Okay. The liquid is coming down, and remember that this liquid is much cooler, and it is coming from the solution heat exchanger. So, its temperature is always lower than the vapor temperature. So, the hot vapor comes in contact with the strong solution in this column. Okay. What happens then? So, you can see this in the enthalpy composition diagram. This is the state of the vapor at this point. Okay. State of the vapor at this point. Okay. That means at the lower portion of the rectification column. This vapor comes in contact with the solution that is entering into the rectification column. And what is the state of the solution that is entering into the rectification column? That is this. Okay. So, that you can see that there is a temperature difference between the vapor and the solution, and the vapor is much hotter than the solution. As a result, heat transfer takes place from the vapor to the solution, and in this process the temperature of the vapor reduces and the temperature of the solution increases. Simultaneous to heat transfer, you also have mass transfer. Okay. How mass transfer takes place? When heat is supplied to the solution that is coming into the system, some ammonia vapor is generated. Okay. That means ammonia is generated from the solution, and this ammonia vapor will be mixed with the vapor that is moving up. So, you can see that as the okay. So, as the vapor is moving up, its state is shown by this arrow here. That means it becomes progressively rich in ammonia. So, okay, so you can see that its concentration varies from this point to this point. That means it gets enriched in ammonia, and at the same time its temperature drops because of the heat transfer. Simultaneously, what happens is, since you are stripping this solution of ammonia, obviously its concentration has to drop. So, you can see that its concentration is decreasing in this direction. Okay. That means the vapor concentration increases in this direction and the solution concentration decreases in this direction. Okay. So, the net effect is that the vapor becomes rich in ammonia and the solution becomes weak in ammonia. Okay. So, that is what is shown in this process. Okay. How the temperature increases, and if this rectification is perfect, you will find that at this point the strong solution that is entering into the system will be at equilibrium with the vapor that is leaving the system. That is what is shown here. Okay. So, this solution this vapor is at equilibrium, this liquid is in equilibrium with vapor that is leaving the system. Okay. Of course, in actual case this is not possible, because for perfect rectification and perfect equilibrium you require an infinite column. So, in an actual system you will find that there is no equilibrium is not there. Okay. One advantage of this particular system is that you can see that some of the heat is transferred from the hot vapor that is coming from the generator. Okay. And this heat is given to the solution that is going to the generator. That means the solution that is going to the generator is getting preheated by extracting heat from the vapor. Okay. This is beneficial because obviously this will reduce the required heat input in the generator. Okay. Otherwise, if, let us say that if this is not there, then it has the entire heat has to be supplied by the external medium in the generator itself. Okay. And this is wasteful, because ultimately the vapor has to go to the condenser, and the heat will be rejected in the condenser to a low temperature heat sink. Okay. So, instead of throwing it to the low temperature heat sink, you are extracting some of the heat from the vapor before it goes to the condenser. Okay. So, this is good as far as the system COP is concerned. Okay. So, ultimately what has happened in this particular lower portion of the rectification column and the generator is that there is an exchange of heat and mass between the vapor and the liquid. Okay. During this process, vapor becomes hot and it becomes weak in ammonia, and the liquid becomes hot and weak in ammonia, and the vapor becomes cool and rich in ammonia. Okay. Okay. So, that is what I have summarized here. Heat and mass transfer takes place between the ascending vapor and descending liquid, and ascending vapor is enriched in ammonia and descending liquid becomes weak in ammonia, and in an ideal case vapor leaving will be in equilibrium with liquid entering. Solution entering the generator is preheated. So, this is beneficial as required heat input is reduced. Now, let me explain the deflegmator or reflux condenser. Okay, so this shows the upper portion of the rectification column plus the deflagmator. As you know that this is the deflagmator D. Okay, what is happening in this one? The vapor that is entering into the deflagmator is nothing but the vapor that is leaving the lower portion of the rectification column. Okay, so that enters into the deflagmator, and let us say that it moves up, and at the upper portion it rejects some heat to the low temperature heat sink. Okay, so this is the heat rejected in the deflagmator QD. So as a result, some liquid condenses. Okay, and this condensed liquid, which is called as reflux, moves down. Okay, so the liquid is moving down and vapor is going up. Okay, and this vapor temperature is much cooler than the liquid temperature. So again, there will be exchange of heat and mass between the vapor and the liquid. Okay, so the net result is that at the end of this column you have a very pure ammonia. Okay, which goes to the condenser and the refrigerant circuit. Again, this is shown in the temperature composition diagram. You can see that zeta SV, this is the condition of the vapor that is entering into this column, and as it comes in contact with the reflux, you can see that its temperature drops, and at the same time it is getting rich in ammonia. Okay, so you can see that finally it leaves at this concentration, which is much higher than this concentration. Okay, so enrichment of vapor is taking place in this column. At the same time, the liquid again becomes weaker because some ammonia is generated. Since you are taking ammonia out of the solution, obviously its concentration reduces. Okay, so liquid follows this path and vapor goes in this direction. Okay, and since there is heat transfer during this process, liquid temperature increases in this manner and vapor temperature reduces in this manner. Okay, so heat has to be rejected to the low temperature heat sink QD. So again, this is a summary of what I have explained. At the top of the deflagmator, heat is removed from the vapor, so that a part of the vapor condenses, which is known as reflux. This reflux, that is cooler, exchanges heat with the hotter vapor ascending in the column. During this process, water vapor is transferred from the vapor to the liquid, and ammonia is transferred from liquid to the vapor. And vapor leaves the rectification column in almost pure ammonia form with a concentration of greater than 99%. Now, what do we, so far we have explained the working principle of rectification column, but how does it look like, or how do you design it? So the rectification column could be in the form of a packed bed, or a spray column, or a perforated plate column. Why do we need a packed bed or spray column or a perforated plate column? Because we need to have what is known as a large residence time, so that the fluids can spend more time together, so that there will be high heat and mass transfer rates, so that ultimately you get almost pure ammonia vapor at the exit of this rectification system. Okay, so you have to have a higher heat and mass transfer rates. So you cannot simply have a hollow tube in which liquid and vapor comes in contact, because in such case there will not be enough time for heat and mass transfer to take place. Okay, so if you want to design it properly, you have to have something like a packed bed or a perforated column or a spray column. Okay, so that liquid comes in intimate contact with the vapor and heat and mass transfer can take place. Okay. Now let us briefly look at the steady flow analysis of the system. This is carried out in a manner similar to water lithium bromide system, that is by applying, remember that for water lithium bromide system we have carried out the steady flow analysis by applying heat and mass balance across each component. Okay, for example, if you have to do this for ammonia water systems, what you have to do is you have to take individual component, apply heat and mass balance. For example, if you take the condenser, remember that if you apply heat mass energy balance to this, you will find that QC is equal to mass flow rate of refrigerant into H10 minus H11. Okay. Similarly, you can do an energy balance for the evaporator. You can also do an energy balance for the heat exchanger. Okay, energy coming in is energy going out, since it is a steady flow process. Similarly, you can do steady flow energy balance for the other components like solution pump, solution heat exchanger, absorber and all that. Only difference between this system and ammonia water system is at this point. Okay. Of course, this point is also the solution heat, the subcooling heat exchange is also different, but this analysis is fairly simple. Okay. What is the major difference is in this portion. Okay. So, I will show you how steady flow analysis has to be carried out for this portion, so that you can evaluate the performance of this particular system. So, and there is one difference here in water lithium bromide systems. When we say strong solution, that means the solution that is strong in the lithium bromide, okay, and weak solution means solution weak in lithium bromide. Whereas in ammonia water system, the meaning of strong and weak solutions are different. When I say strong solution in ammonia water systems, that means the solution that is strong in ammonia, okay, that means that is rich in ammonia. Strong solution and rich solution are same. Okay. Similarly, weak solution means the solution that is weak in ammonia. Okay. So, if you are applying this nomenclature, strong solution means the solution that is leaving the absorber in this case, whereas in water lithium bromide case, strong solution means the solution that is entering into the absorber. So, you have to keep this difference in mind. Since we are defining strong and weak solutions in this manner, the definition of circulation ratio will be different, and also the expression for circulation ratio will be different. Okay. So, what is the expression for circulation ratio? Okay. So, circulation ratio here is defined as the ratio of weak solution to refrigerant flow rate. Okay. So, weak solution is m dot Ws, refrigerant flow rate is simply m dot. Okay. So, circulation ratio lambda is equal to m dot Ws by m dot. This implies that the weak solution flow rate m dot Ws is equal to lambda into m dot, and strong solution flow rate is nothing but 1 plus lambda into m dot. This you can easily get by applying mass balance across the absorber. Okay. And from mass balance across the absorber, you can also show that if you are assuming pure ammonia is circulating in the refrigerant circuit, you can write the expression for circulation ratio in terms of strong solution concentration zeta S and weak solution concentration zeta W. Okay. So, this expression is different for water and lithium bromide system and for ammonia water system. So, this is one difference you must keep in mind while performing calculations. Okay. So, due to the presence of rectification column with defragmenter, equations for mass and energy balance will be different for this system. Okay. How they are different, let us see. So, what we do here is we take a control volume, this is the control volume, across the complete entire rectification column. Okay. That means I am taking the entire rectification column. Okay. So, this includes the generator here and the rectification column here and the defragmenter. Okay. So, defragmenter D, rectification column R and the generator G are all taken into this control volume. Okay. And then you apply the mass and energy balance to this control volume. If you are applying the energy balance to this control volume, Qg minus Qd is the net heat transfer into the control volume, because you are supplying heat Qg at the generator and you are rejecting heat Qd at the defragmenter. So, Qg minus Qd is a net heat input into the system by way of external heat supply. This should be equal to the energy leaving the control volume. And what is the energy leaving the control volume? Energy leaving is nothing but energy carried by the vapor at point 10 and energy carried by the solution at point 6 minus energy coming into the control volume by way of mass flow. Okay, that is 4. So, you can easily write energy balance Qg minus Qd like this. Okay. And again m dot 10 is nothing but your refrigerant flow rate m dot, if you are assuming perfect rectification. And what is m dot 6? M dot 6 is nothing but your weak solution, okay, m dot Ws, and m dot Ws, as you have seen just now, is nothing but circulation ratio into mass flow rate of refrigerant. And m dot 4, that is this, okay, m dot 4 is nothing but your strong solution flow rate, and strong solution flow rate we have seen just now is nothing but 1 plus circulation ratio into refrigerant flow rate. So, if you are substituting these expressions in this one, you can finally show that Qg minus Qd is equal to m dot into H10 minus H4 plus lambda into H6 minus H4. So, this is the expression for okay. So, this is the expression for net heat flow into the control volume. Now, from the above equation we can calculate Qg minus Qd, but if you want to find out the COP you need to know Qg, because that is finally the heat input to the system. Okay. So, first calculate Qg minus Qd using the above energy balance equation for the control volume, then you have to calculate somehow Qd, so that finally you can get Qg. So, how do we do this? So, this requires estimation of heat transferred in the deflagrator. Obviously, you have to find out what is the heat transfer to the heat sink in the deflagrator, that is Qd. Okay. And this can be obtained by applying mass and energy balance across the deflagrator section. So, I will show you the deflagrator section now. Okay. So, what we are doing here is I have taken a control volume, this is again a control volume across the deflagrator section. You know, remember that this is your deflagrator and this is a part of your rectification column. You can take this control volume at any place, you can include any cross section here, okay, but the outlet here must include the vapor, okay. And you can show by from mass and energy balance for this mass and energy balance. Okay, for this control volume you can show that you can arrive at this expression Qd by m dot. Qd is the heat rejected in the deflagrator divided by m dot. M dot is the refrigerant flow rate from the system. So, Qd by m dot is equal to HIV. HIV is nothing but the vapor enthalpy at any cross section minus H10. H10 is nothing but the enthalpy of the refrigerant vapor leaving this section, plus 1 minus zeta IV divided by zeta IV minus zeta EL into HIV minus HEL. What is zeta EL and HEL? Zeta EL and HEL are the enthalpy and the composition of liquid that is descending in this section. Okay. So, zeta EL and HEL refer to the liquid properties, the liquid that is descending. Remember that in this section liquid is descending and vapor is ascending. Okay, vapor is ascending, they exchange heat and mass. So, you can arrive at this expression easily by applying mass and energy balance. So, finally, this is written as HIV minus H10 plus HL. Okay. So, if you are plotting the same thing on enthalpy composition diagram, you can show that I am plotting this on enthalpy composition diagram. What I have done is I have marked the condition of the vapor that is ascending and the liquid that is descending at any cross section. Okay. So, that is shown by point V and L, and then I have joined the points V and L by a straight line. Okay. You join it by a straight line and you extend this straight line so that it intercepts this xi is equal to 1 line at this point R. Okay. This is an important point R. Okay. So, this point R I will show you later is known as pole of the rectifier. Okay. So, from the expression shown earlier, it can be very easily shown that the distance between this point R and this point is nothing but Qd by m. Okay. Remember that this analysis is based on the assumption that the vapor that is leaving the section is pure refrigerant. That means you are assuming that vapor is leaving at a concentration of 1. Okay. If you are assuming that, then this vertical distance is nothing but Qd by m, and this distance is equal to HL. Okay. What is HL? Okay. So, HL is this. Okay. This is HL and this is given by this expression. Okay. Whatever is there in the bracket, that is 1 minus zeta IV divided by zeta IV minus zeta EL and HIV minus HEL. And what is this? You can easily see from the above, from enthalpy composition diagram, that HIV minus HEL divided by xi IV minus xi IL. Okay. This is nothing but the slope of the line. Okay. Let me show that. So, this is nothing but the expression in the bracket is nothing but the slope of this line. So, obviously, the slope of that line into this distance will give you the enthalpy difference between this point and this point, that is known as HL. Okay. So, this is how you can plot the enthalpy composition diagram of this deflagmator section, and you can arrive at these points. Now, how do we calculate QD? Because ultimately we would like to calculate QD. Okay. So, point R, as I said, is called as pole of the rectifier, and it can be shown easily that the ordinate of pole R is equal to QD by M plus H10. Okay. So, H10 is nothing but the enthalpy of the vapor leaving the deflagmator section, which can be easily obtained from refrigerant property table. So, you know H10. So, if you can find out the ordinate R, then you can easily find out QD by M dot. Okay. So, this is the principle, and as I have already said, this HL is equal to this quantity, where this one is your slope of the line, that multiplied this will give you the enthalpy difference. And it should be noted that the line joining points L and V on enthalpy composition diagram need not be an isotherm. What it means is that points V and L need not be in equilibrium with each other. That means we have drawn the enthalpy composition diagram by not assuming any equilibrium or anything. You need not assume anything. Okay. So, you simply say take one section of the lower part of the deflagmator and then simply apply the energy and mass balance, and the V and L need not be in equilibrium, but they have to satisfy the mass and energy balance. So, that is the only requirement. Okay. And for rectification to proceed, it is essential that at every cross section the temperature of the vapor should be higher than that of the liquid. This is an essential condition, otherwise rectification cannot proceed. That means the vapor should always be hotter than the liquid. So, this is possible only if the slope of the line passing through the pole R is always steeper than the isotherm in the two phase region passing through the liquid state points HEL and zeta EL. Okay. So, this condition has to be met. That means when you are taking out some heat in the deflagmator, you have to make sure that the line joining the points V and L are always steeper than the isotherms in the two phase region. Okay. Only then vapor will be hotter than the liquid. Okay. Only when vapor is hotter than the liquid, then heat transfer can take place from the vapor and liquid, and the mass transfer can take place from the liquid to vapor. Okay. So, this has to be ensured, and this has to be ensured only by controlling your heat rejected in the deflagmator. Okay. As I said, this can be placed ensured by placing the pole R at a sufficiently high level on the zeta is equal to 1 axis, and this in turn fixes the minimum amount of reflux and the heat rejected at the deflagmator. It is observed that for ammonia water mixers, the condition that the vapor must always be warmer than the liquid is satisfied by drawing a straight line through R steeper than the isotherm passing through the strong solution feed point 4. So, that means what you have to do is normally from the properties and from the operating temperatures and pressures, we know the condition of the feed. What is the feed? Feed means a strong solution that is entering into the rectification system. Okay. So, you know the condition of that. So, you can mark that point on the enthalpy composition diagram. Okay. So, first mark the condition of the feed on the enthalpy composition diagram, then draw an isotherm passing through this point. Okay. And then you have to choose the condition of the pole in such a way that the line joining the vapor and liquid points at any part of the deflagmator section is steeper than the isotherm passing through the feed point 4. Okay. So, this is what you have to do. Okay. Once you do this, you can find the pole, because pole is nothing but the interception between the point joining the vapor and liquid, and the zeta is one line. Okay. So, you can find out the position of the pole. Once you find the position of the pole, you can find out QD by M. Okay. And why are we doing this? Because we want to find out QZ, because you know QZ minus QD, and if you know QD, you can find out QZ. Okay. So, this is the procedure here. A complicated procedure. The position of R is fixed from this, and the minimum amount of deflagmator heat QD minimum is determined. However, we find that in actual case, the actual deflagmator heat will be larger than the minimum amount obtained in this manner. Okay. And the ratio of minimum deflagmator heat to actual deflagmator heat is called as rectifier efficiency eta R. So, rectifier efficiency eta R is defined as QD minimum by QD actual. So, QD minimum can be determined from the procedure explained now, and you have to know eta R so that you can find out QD actual. And it is observed that the rectifier efficiency eta R depends on the design of contact surface used for the rectification column. That means what kind of a surface you are using. Is it a plate column, or is it a packed bed or is it a spray column. So depending upon that you have to find the eta R, and once you know the eta R and QD minimum, find QD actual. Okay, so this is the procedure. So thus to evaluate the actual performance, details regarding rectifying column are required. You must have noticed that the calculations for ammonia water systems are much more complicated compared to water lithium bromide systems. All this complication is coming because of the lower boiling point temperature difference between ammonia and water, but this is something which cannot be avoided. Okay, because if you neglect this, you find that there is a lot of water in the refrigerant circuit, and if you do not consider the presence of water there, then first of all the system may not function properly and the calculations will be different from the actual calculations. Okay. So, if you want to predict the performance properly, you have to have the details of the rectification column, the constructional details and all that, and then you have to carry out this complicated analysis presented now, and only then you can arrive at reasonably accurate values. Okay. Sometimes the details may not be available and you have to do calculations without these details. So, what is done in such cases is when you, in the absence of required data, the COP is calculated by assuming that the deflagrated heat is a certain percentage of generator heat. Okay. So, normally you take a value of about 10 to 20%. That means what you do is you carry out the steady flow analysis of the system, okay, taking the control volume across the entire rectifying system. Okay. So, as we have seen, that will give you QG minus QD, okay, which can be obtained easily. Then you assume that QD is a certain percentage of QG. Okay. If you are making this assumption, then you can calculate QG. Okay. So, this is a faster way of calculating. Of course, this is not very accurate and you also have to know what is this percentage. So, normally a value of 10 to 20% is taken in actual calculations. Okay. Now, let us the systems discussed so far, both water lithium bromide systems as well as ammonia water systems are known as conventional absorption refrigerant systems, and you have seen that they do not run purely on heat, because you also have to have certain amount of mechanical energy to run the solution pump. Okay. So, they are not purely heat operated systems, because certain amount of mechanical energy is also required. Okay. So, you also have absorption systems known as pumpless absorption systems. Okay. As the name implies, a pumpless absorption refrigerant system does not have a pump. Okay. Let us look at some of these systems and what are the features of these systems. So, as the name indicates, these systems do not need a mechanical pump. And what are the advantages of not having a pump? The advantages are high reliability with little maintenance due to absence of moving parts. So, in a pumpless refrigerant system, you do not have a moving component at all. Okay. So, once you do not have any moving component, reliability will be extremely high. Okay. Because there is, frankly speaking, there is nothing that can go wrong in a pumpless system. Okay. And practically no servicing is also not is required. Okay. So, no maintenance is required, no servicing is required, and very high reliability. Okay. So, this is one major advantage of pumpless system. Okay. And since you do not have any moving parts, the operation will be perfectly silent. In fact, you do not know whether the system is working or not, because it does not make any noise. Okay. Only when you feel the inside, you know that it is working. And a wide variety of heat sources can be used to run the systems. So, what are the applications of pumpless systems? The applications are as refrigerators for remote and rural areas, in portable refrigerators, and as refrigerators for luxury hotel rooms, etc. Okay. In luxury hotel rooms, the customers do not want to have any noise. Okay. So, it has to be perfectly noiseless inside the room. Okay. So, if you are using a normal mechanical vapor compression system, the compressor will be making noise. Okay. So, sometimes this will be disturbing. Okay. So, in 5-star hotels and all, they use the pumpless absorption systems. As I said, since it does not have any moving components, it does not make any noise. Okay. So, this is one of the major applications of pumpless absorption systems. Okay. There are several pumpless systems using both water lithium bromide and ammonia water. Okay. So, people have been working on these systems for the last many decades. But out of these systems, the most popular one is what is known as Platen-Munter system or triple fluid vapor absorption refrigerant systems. Okay. So, let us look at Platen-Munter systems now. Platen Munter system, if you remember from our first lecture, is the name of the inventors, Platen and Munters, and this system uses ammonia as refrigerant, water as absorbent, and a third fluid, hydrogen, as the inert gas. That is the reason why you call these systems as triple fluid vapor absorption systems, okay, because you have 3 fluids. Unlike conventional systems, the total pressure is constant throughout the system. So, since the total pressure is constant throughout the system, you do not require a compressor or pump for pressurizing. Okay. So, you at the same time you also do not require any expansion valve, because the entire system operates at a single pressure. So, you do not require anything for pressurizing the working fluid. Okay. So, this is the major principle behind these systems. Okay. So, no need for mechanical pump. And to allow the refrigerant to evaporate at low temperatures in the evaporator, an inert gas is introduced into the evaporator absorber of the system. Okay. So, if the you have to, when you are discussing pumpless systems, particularly Platen Munter systems, you have to make a distinction between total pressure and partial pressure. So far we have been talking about the pressure. Okay. So, in this particular system you have a partial pressure and a total pressure. Okay. So, the total pressure is same inside the system, inside the entire system, okay, but the partial pressure will be different. Okay. So, let us look at this. Let me first explain the principle. Okay. So, this is a schematic of typical Platen Munter system. This consists of a condenser, an evaporator, an absorber, a generator here, and another component called as bubble pump. Okay. For the sake of simplicity, I have not shown the rectification column, deflagmator and all that, but in an actual system those things will be there. Okay. So, we are assuming that we do not have any of those things. At the same time, we are getting pure ammonia at the end of this bubble pump. Okay. So, let me explain the working principle starting with this point. So, at this point you have pure ammonia refrigerant, okay, and this is at a high pressure. So, this pure ammonia refrigerant at high pressure enters into the condenser, where it rejects the heat of condensation, okay, and what you have at the exit of condenser is liquid ammonia, okay, liquid ammonia at high pressure. Now, this liquid ammonia at high pressure enters into the evaporator. Okay. So, in the evaporator, in addition to ammonia, we also have a third fluid called hydrogen. Okay. So, you have pure hydrogen here, right. In fact, this pure hydrogen makes up for most of the pressure in the evaporator. Since total pressure is same, for example, pressure at this point is, let us say, 15 bar. Okay. So, 15 bar liquid is entering into the evaporator, and inside the evaporator the partial pressure of hydrogen is 14 bar, let us say. Okay. So, hydrogen is exerting a partial pressure of 14 bar here. So, 14 bar is because of hydrogen. So, what will be the pressure of ammonia here? The pressure of ammonia has to be the partial pressure of ammonia, because the total pressure is constant. So, in evaporator section you find that P total is equal to P ammonia plus P hydrogen, okay, and the P total, as we have seen, is equal to 15 bar, and out of this 15 bar hydrogen is making up for the 14 bar. Okay. That means the partial pressure of ammonia has to be 1 bar. Okay. So, there is a sudden, this is somewhat similar to an expansion, but it is not expanding by throttling or anything, but it is by simply expanding by simply entering into a vessel where a third fluid is exerting a major portion of the pressure. Okay. So, during this process the ammonia pressure drops from 15 bar to 14 bar. So, here you have liquid ammonia at 1 bar. 1 bar ammonia liquid. Okay. Now, this 1 bar ammonia liquid can evaporate at very low temperature, because you find that at 1 bar it has an evaporation temperature of about minus 33 degrees centigrade. Okay. So, in the evaporator it can evaporate at minus 33 degrees centigrade by taking heat from the refrigerated space. Okay. So, that is how you get the refrigeration effect. Now, as it evaporates, what happens? A vapor is formed. Okay. So, you see here that at point 3 vapor of hydrogen and ammonia, which are cooler because they are in the evaporator, they go down because of buoyancy. Okay. So, this vapor consisting of ammonia and hydrogen goes to the absorber. In the absorber, what happens is the weak solution that is coming from the bubble pump. Okay. The weak solution coming from the bubble pump comes in contact with the mixture of hydrogen and ammonia. Okay. So, when they come in contact, what happens is ammonia is taken out from this mixer. That means this solution absorbs ammonia and it cannot absorb hydrogen. So, hydrogen is left out and ammonia is absorbed. Okay. And in this process hydrogen temperature increases. Okay. Since its temperature increases, it becomes lighter and it moves up to the evaporator. Okay. So, that is how the hydrogen circulation is maintained from. So, you have a closed hydrogen circulation from evaporator to the absorber because of the buoyancy effects. Okay. Now, what happens to the solution? Here you have solution now which is now stronger in, this is a strong solution, stronger in ammonia. Now, this is also at 15 bar. So, this goes to the generator. In the generator heat is supplied. So, when heat is supplied in the generator, vapor bubbles are generated. Okay. So, you have vapor bubbles generated in the in the generator, and vapor bubbles, because of the buoyancy, they move up. So, as they move up, they carry some liquid along with them. Okay. So, that is the function of the bubble pump. So, in what are we doing in a bubble pump? In the bubble pump, the vapor bubbles move the liquid from the bottom to the top because of buoyancy. Okay. So, this goes on till the end of the top of the bubble pump. At the top of the bubble pump, liquid goes down because of the gravity and vapor moves up because of the buoyancy. Okay. So, that is how the whole system works, and you can see here that we are rejecting heat at absorber, rejecting heat at condenser, supplying heat in the form of low temperature heat at evaporator, and high temperature heat input takes place at the generator. In addition to that, you also have to supply certain energy for the bubble pump to operate. Okay. So, here energy is required for generating the vapor as well as for operating the bubble pump. Okay. And remember that the total pressure is constant at every point. When I say constant, there will be small differences because of the gravity heads and all. For example, if you look at this one, pressure at this point will be higher than the pressure at this point because of gravity head. Okay. So, this is the working principle of this, and refrigeration is produced as the partial pressure of ammonia in evaporator is much smaller than the total pressure due to the presence of hydrogen, as I have already explained. And if I am just giving an example, if the total pressure, as I said, is 15 bar, then it can condense at 38 degrees centigrade, and the partial pressure of hydrogen is 14 bar. So, partial pressure of ammonia is 1 bar in the evaporator. That means it can evaporate at a minimum temperature of minus 33 degrees centigrade. Now, the liquid ammonia in the evaporator cannot boil in the evaporator as its partial pressure is lower than the total pressure. So, this is one subtle difference is there between this system and the earlier system. Here, because of the presence of hydrogen, boiling cannot take place. What takes place is evaporation. That means, you will not find any vapor bubbles here, simply the ammonia liquid evaporates into the hydrogen gas. So, this is somewhat similar to the evaporation of liquid water in atmosphere. Okay. This takes place as long as hydrogen gas is not saturated with ammonia, and the ammonia vapor generated is carried away by the process of diffusion. Hence, plate and muter systems are also called as diffusion absorption systems. Sometimes people use the name diffusion absorption systems for plate and muter systems. So, as I said, why do we call it as diffusion absorption system? Because here the process is not one of boiling, but it is one of evaporation and then diffusion. Okay. So, this is a subtle difference, right. So, that is why we call it as diffusion absorption systems. Okay. Due to the evaporation process, the temperature of the evaporating liquid changes along the length of the evaporator. This is another difference. You will find that inside the evaporator, the temperature is not constant. Okay. You have a cold region and you have a progressively increasing region with the progressively increasing temperature, and the coldest part is obtained at the end where hydrogen enters the evaporator. So, why this part is coldest? Because at this part the partial pressure of ammonia is least. Okay. So, it can evaporate at lowest temperature. This can be beneficially used to provide two temperature sections in the evaporator. For example, if you are using this system for a refrigerator, you can use the coldest part for frozen food storage and the relatively warmer part for fresh food storage. This is what is done in commercial refrigerators. And the circulation of fluids inside the system is achieved, as I said, due to the effects of buoyancy and gravity head. And a liquid fill is required at the end of the condenser to prevent the entry of hydrogen gas into the condenser. That means, at this point you have to have a liquid field. Okay. If you do not have this liquid field, what happens is some of the hydrogen can enter into the condenser. Okay, hydrogen can enter into the condenser. To prevent the hydrogen entry, we have to provide a liquid field. Okay, gases other than hydrogen can also be used. Even though the original system used hydrogen gas, people have also tried other gases such as helium. And plate and motor systems are simple and good in many ways. One major disadvantage of this system is that they offer very low COPs, okay, and the COPs are of the order of 0.15 to 0.2, and this is because of the energy requirement of bubble pump and also due to various irreversibilities. One such irreversibility is due to the cooling and heating of hydrogen gas in the evaporator absorber section. And additional heat exchangers are used in commercial systems to improve COP. Okay, commercial systems will be different from the schematic shown earlier. Okay. However, in commercial systems, a wide variety of fuels such as electrical heaters in small systems, or you can also use natural gas or LPG or kerosene in larger systems. Okay. Again, let me okay, a typical, as I was mentioning, of the heat exchanger part, you can have in a commercial system, you can have a heat exchanger here, where the cold vapor that is going to the absorber section can transfer heat, can take heat from the hot vapor that is going to the hot hydrogen gas that is going to the evaporator. So, you will have one heat exchanger here. Okay. Similarly, you can have another heat exchanger here. Okay. So, that means you can preheat the solution that is going to the generator. Okay. And the heat source here can be anything. You can use, for example, LPG gas, or you can use natural gas. You can also use kerosene. You can use hot water, or you can use hot oil or anything. Okay. And let me very briefly explain solar energy driven systems. I will not explain, but I will just state absorption systems can also be run purely on solar energy. If you are using a conventional system, then the solution pump which requires mechanical energy can be driven using a turbine driven by the high pressure vapor generated in the generator. That means you can have a turbine which utilizes some of the high pressure vapor generated in the generator, or you can also use photovoltaic cells and have a motor and run the pump using that motor. Okay. And if you are using a pumpless system, of course you do not require any mechanical energy, and you can operate it purely on solar energy alone. And solar energy driven refrigerant systems can also use what is known as solid adsorbents. Okay. Some of the examples of solid adsorbents are water silica gel, where water is the refrigerant, silica gel is the adsorbent, water zeolites, zeolite is adsorbent, methanol like activated carbon system, methanol is the refrigerant and activated carbon is the refrigerant, ammonia calcium chloride system, hydrogen metal hydride systems. Okay. However, these systems have not been commercialized on a large scale. Let me just show a table where compression systems are compared with absorption systems. Okay, so this table shows the comparison between compression and absorption systems. So you can see that compression systems are work operated, absorption systems are heat operated. Compression systems offer high COP, absorption systems offer low COP. Now let me quickly summarize what we have learned in this lesson. In this lecture, working principle of ammonia water systems is explained. Principle of rectification is discussed. Method for evaluating steady state performance is presented, and pumpless systems are discussed, and solar energy driven systems are mentioned, and finally comparison is made between compression and absorption systems. In the next lecture we will look at some of the problems on compression and absorption systems. Thank you.